Hello everyone and welcome to MV Tutors. I hope that you're all doing good. We're going to have a look at the Gauteng Prelim, Physics Paper 1, or rather Physical Science Paper 1, which is the physics portion. I hope the preparations have been going well and all the best with your exams. Now we see this was a 3-hour paper out of 150 marks. If we take that 3 hours and convert it to minutes, we have 180 minutes divided by the marks. We see that we need to spend at most 1.2 minutes per mark. Okay, so now we're going to look at question 1, which counts, 20 marks. So how long should we be spending? We should be spending 24 minutes. Anything more than that, we move on. All right. Okay. So 1.1. The diagram below shows a trolley held stationary on a slope by a spring force that has a reading of X newtons. The weight of the trolley is W and there is friction F between the trolley's wheels and the slope. Now the reading on the spring balance is, okay, so let's just have a look at our trolley. All right, they told us that the weight is W and we know that's our normal force. We have the force of friction. I'm just going to say F. Actually Fs because it's stationary, static friction. And if I were to resolve the weight component, or rather the weight into its components, on this portion here, I would have the weight cos 30, and over here, I would have the weight sine 30. All right, and there's also the force by the spring, okay? And so because of that, this is where that, because this spring is sort of like pulling the trolley upwards, if you may, okay? And the weight of the trolley is pulling it down. So now that they're stationary, we're going to represent that with a longer arm and say that is the force of the spring, okay? Which is what we need to read, all right? And now it says the reading on the spring balance is, so if I were to sum my forces, okay, in the X direction, they're going to equal to 0 because the net force is mass times acceleration, and because this is held stationary, the trolley is stationary, there is no acceleration, so we're going to have the net force is equal to 0. And if I take upward as positive, I'm going to have my force due to the spring, the static friction. Maybe I shouldn't have used Fs. Maybe let me say for the force of friction, let's rather use Ff. Okay, just to say it's the force of friction. Okay, now what am I doing? I need to get a less, yes. Okay, so this is the force of friction. And I'm going to subtract my weight component on the parallel side. Okay, and that's equal to 0. Now, the force of the spring, that will be red, instead of X, it will actually be the weight sine 30 minus the force of friction. So this is what X is equal to. Now, as I look over for the options that I have, the closest is C, where we have the weight component minus the friction force, okay? But the sine 30 is required. So this is, this is a little bit tricky. I feel like our answer is not here because D is incomplete. Even C is incomplete. Okay, so if I were to be writing, I would say C and then correct them and say, actually, it should be W sine theta minus the friction force, not just W by itself. Okay, so we'll go with C here. All right. If you have opposing views, please do comment below. Now it says a box M is being pushed horizontally at a constant velocity. So since the velocity is constant, I'm just going to say the acceleration is 0. So it's been pushed horizontally at a constant velocity on a rough surface by a force F. So while you have the force, you have your friction force as well, because it's a rough surface. Now it says if the force F acting on the box decreases, then the frictional force acting on the box decreases. Well, I think it will increase. I think the frictional force will increase. Okay, because this force is decreasing. Yeah, because the force applied is decreasing, then you'll have more friction to deal with. Okay, so I don't think A is the right answer. B, velocity of the box decreases, most definitely. Yeah, it will decrease. Okay, so I will go with B. And the acceleration of the box increases. No, I don't think so. No, I wouldn't go with that, because I mean acceleration force is equal to ma, right? A is equal to F over m. So if your force decreases, your acceleration should decrease, because those two are directly proportional. So I wouldn't go with C. And then the normal force increases. Well, the normal force really depends at this point on the mass of the box. So if the mass stays the same, I don't see the normal force changing. So in this case, I will go with B as the answer. All right, 1.3. Yeah. So a ball is dropped from a height of 5 meters. So let's just say we have the ball, and then from the ground, we have there 5 meters. Okay, if it's dropped, it means the initial velocity is 0 meters per second. Or rather, the way you are taught to write it is like that. Okay, while we're at it, guys, please don't forget to like our videos and subscribe to our channel. Alright, so a ball is dropped from a height of 5 meters. After it falls 2 meters, it reaches a velocity of v. Okay, so let's say this is 1 meter that has been dropped, 2, 3, 4, and then finally at the bottom 5. So when it reaches here, after it has been dropped 2 meters, the velocity is v. Now, which of the following statements is correct? After it falls 3 meters. So at this point here, what is happening? The velocity of the ball is 3 meters per second. We have insufficient information to actually calculate the velocity at this point. Okay, so because all we know is that it was dropped, so we have the initial velocity, we have the height. Okay, actually, let's see. Let's not dismiss it. So if I wanted to know the final velocity, I have the initial, which is 0. I don't have time. Okay, here, actually, yeah, we could calculate the final velocity using the final velocity squared. Okay, let's just entertain the idea, because in an exam you want to be sure. So I'll have a square root. Square root 0 squared plus 2 times 9,8 times 2, because it's all going down. If I'm taking down, it's positive. Okay, so no, the velocity there is definitely not 3. It's 6,26. Okay, we checked. And we had enough information. So, yeah. And then, oh, they said after it falls 3 meters. So, yeah, we can change the 2 to 3. It's definitely possible. So, we can just check here. So, yeah, even no. So, that's 7,67. So, no. The acceleration of the ball is 3 meters per second squared. No, this is free fall. All right. So, the only, the force acting on this projectile motion is gravitational force, and the acceleration should be 9,8. like it says on C. So the acceleration is 9.8. That is true. The velocity of the ball is that? No. So C in this case would be the correct answer. Now 1.4. In which of the following rows does the type of collision match with total momentum and kinetic energy? Okay, so I see the type of collision is either elastic or inelastic. When it comes to elastic collision, okay, we know that linear momentum, so total linear momentum is conserved. Okay, so momentum is conserved. And we also know that the total kinetic energy is conserved as well. So kinetic energy is conserved. But when it comes to non-elastic collision, we know that linear momentum is conserved, but the total kinetic energy is not conserved. So if you know that, you're going to go to that table and see which one is applicable. Okay, so A for elastic, both have to be conserved, so that is out. If we have a look at A as well as D, we are cancelling those. We're not looking at them because they're wrong. But when it comes to inelastic, total momentum has to be conserved. So C is out and we're left with B. Okay, so total momentum is conserved. That is true. Kinetic energy is not conserved. That is true. So our answer for 1.4 is B. And 1.5, a block slides over a rough horizontal surface. Okay, so there's friction, and eventually stops after 1.5 meters. Which of the following statements is false for the movement of the block? The net work done on the block decreases its kinetic energy. Okay, so they're talking about net work. We know that net work is equal to force times displacement cos theta. All right, so this block slides over a rough horizontal surface. So if it's a rough, you have this force that was probably applied, and you have your frictional force over there. The distance was 1.5, and probably yeah, this would be cos 0. Okay. So reading the statements again, the net work done on the block decreases its kinetic energy. So we know that this thing is coming to a stop eventually, all right? So when it comes to kinetic energy, or the change in kinetic energy, we know that it's the final velocity minus the initial velocity. So ultimately, our change in kinetic energy will be a negative value because our final velocity will be 0. Okay, and then the net work done on the block decreases its mechanical energy. So mechanical energy is basically the change in kinetic plus the change in potential. And there isn't really potential energy here because there's no vertical motion. So that would cancel out and we're back to our change in kinetic energy, which, we're going to get a negative answer. And then the net work done on the block is negative. I would say so. Would it? Because the force applied, well, yeah, we don't know what force was applied, but we do know that there is friction which ultimately causes this block to come to a stop. So does it mean that the net work done is negative? If the friction force is bigger, then yes, it would be. Let's get back to it. And then D, the block is slowing down. Okay, obviously it is slowing down because eventually it stops. So now it says, which of the following statements is false for the movement of the block? All these statements sound true. Okay, so again, just like with 1.1, I'm like, I don't really see which one would be false there. Yeah, so yeah, I'm really not sure, guys. I'll come back to 1.5, but I think they're true for the movement of the block. Okay, this is where I'm wasting time. If I check the time, I'm at 14 minutes. I should be way past this question. So let's speed up and make sure that we're done with this question by 24 minutes. Okay, so I'm going to just leave it at that for now. Come back to it if there's time. Otherwise, we move on. 1.6. The diagram below shows the absorption spectrum of an element on hypothetical stars A to D as observed from the Earth. Which star is moving away from the Earth with the highest velocity? Alright, so with the red and blue shift, if it is moving away from the Earth, then we're looking at the red shift. Okay, the red shift, we know that the frequency is quite low. The frequency is the lowest, and the wavelength is the highest compared to the blue. Alright, so which one then, if we look between stars A and D? Well, if I look at the black lines for A, actually, they are more towards the red shift. Okay, so I would go with A. But if I look at B, it's more spread out. They're a little bit faint on the blue side, but there are still some stripes there. So B is more of a blue shift. C as well, there are some lines there on the blue side. D, there's only two lines that I'm seeing that are quite faded out. Okay, but the one that is strongly to the red would be A. Okay, and then 1.7. The diagram below shows 2-point charges where Q1 is positive 5 and Q2 is negative 4 at a distance x from point B. Now, the net electric field at point P in terms of E is given by. Alright, so I would take charge 1, and because it's positive, then your electric field lines are sort of like moving away. Okay, and if I have a look at 2, because it's negative, they are moving inward. Okay, and there you have P somewhere. So if I then, if I were to look at the net electric field in terms of E, I would then take this portion over here. I see it's moving to the right. Even here it's moving to the right. Okay, and so here we have 5E, and there we have 4E, and it's all moving to the right. So we have in total 9E to the right. And the options given there, well, we see that D is the correct answer. 1.8. The circuit below is set up. The battery has an EMF of 9, an internal resistance of 0.2 ohm, and the reading on A1 is 1.8 amperes. Okay, which statement is correct when a charge of 1 coulomb flows in the circuit? Okay, so here I see there's potential difference that is talked about, joules of energy, current. So I'm just going to go ahead and calculate, guys, the EMF, which is equal to your potential difference, terminal potential difference, plus your lost volts. Okay, the EMF was given as 9 volts. Your terminal potential difference, that is what we're actually trying to look for here. Okay, when a charge of 1C flows through the circuit, which statement is correct. Okay, and then the lost volts, it's your current multiplied by your internal resistor or resistance, which is 0.2. Okay, so if I were to calculate the terminal potential difference, it would be 9 minus 1.8 times 0.2, and I would get an answer of 8.64 volts. Alright, so 9 volts is the potential difference across the resistor. No, it's 8.64 volts. 9 joules of energy dissipated by the resistor. No, it's actually 8.64 joules of energy dissipated by the resistor. 8.64 amperes flowing in the circuit. No, they told us it's 1.8. So 8.64 joules of energy is dissipated by the resistor. Yes, that is correct. So D is the correct answer. 1.9. How are we doing for time? 19 minutes. Okay, we managed to catch up. An EMF can be induced across a stationary coil by, well, if you think about your theory from grade 11, actually the EMF is induced in a coil when a bar magnet is pushed in and out of it. Okay, in and out. All right, so here, A, stationary magnetic field. No, I wouldn't go with that. B, using more turns on the coil. No. C, a change in magnetic field. Yes, so as you put it in and out, there is a change in magnetic field. So yes, C, we can go with that. And D, increasing the area of the coil. No. So we will go with C. And then lastly, 1.10. The diagram below shows the energy levels of an atom in electron volts. All right. Now the energy needed to excite an electron from the ground state to the first excited state is, okay, so here, change in energy from the ground state, so that's the initial, to the first excited state, that's the final, so final minus initial. Or in this case, they started at 1. So let's just say E2 minus E1. Okay, so the energy level at, from the ground state to the first excited state, actually, yes, from the ground, that's E1, to the first excited state, that's 4,8. Okay, so from the ground, we have negative 15. Well, here it's going to be negative 4,8 because we're saying the final is the first excited state. And then we have negative 15. Okay, and if we just work that out, we have negative 4,8 plus 15. So that is positive 10,2. Okay, electron volts. And in this case, whenever you go from a lower energy level to a higher energy level, you actually are absorbing. Okay, you'll see your absorption spectra. And if you're going from a high to a lower energy level, you will be emitting. All right, but anyway, getting back to the question, so the energy needed to excite an electron from the ground state to the first excited state is positive 10,2 electron volts, and that is C. Okay, and yeah, that's it with question 1. Yeah, and we finished in almost 23 minutes, so that's great. Question 2. All right. So we have two blocks that are attached to each other by a light inextensible string moving over a frictionless pulley as shown in the diagram below. The slope AB has a smooth surface, okay, so there's no friction there, and makes an angle of 50 degrees with the horizontal. Slope BC, on the other hand, has a rough surface, okay, so there's friction, and makes an angle of 30 degrees with the horizontal. All right, so we can see the diagram there. It's quite clear. Now 2,1, it says state Newton's second law of motion in words. I am not going to write this down. You know this by now. So what does it say? It says that when a force acts on an object, the object will accelerate in the direction of that force. All right. And now let's talk about the acceleration. So that acceleration is directly proportional to the force. Hence, in question 1, I was saying if the force were to reduce, acceleration was also going to reduce. All right. But anyway, so the force is directly, or the acceleration is directly proportional to the force. And in the same light, the acceleration is inversely proportional to the mass. Okay, so that is Newton's second law of motion. Now 2.2. The coefficient of kinetic friction between the slope BC and the block M2 is 0,2. Okay, so we can note that coefficient of kinetic friction. So mu K is 0,2. Now it says in 2.2.1, draw a labeled free body diagram of block M2. Okay, so block M2 is on slope this side. So we always start with what we know, that is always true. Going downwards, it's the weight, or you could say Fg, which is equal to M times G. All right, you don't have to resolve it in its components. You can leave it as is. And then you have your normal force. Okay, I'll just put that as an N. And then you have your tension force. So that is parallel to the slope. Force of tension. I'm just going to put a T there. And there's friction because the natural tendency is for this block to move downwards. So your friction force will act upwards. Okay, but it shouldn't be that big. When you talk about size, I'm just going to say force of friction or kinetic friction, Fk. And then what else do we have? So if you were to resolve the force of gravity in its components, you would see that actually what is trying to take down the box is the force of gravity, that's the parallel component, but you don't have to put that there. It's fine. You can leave this as it is. And we have 4 forces. I'm probably thinking that's 4 marks. Yeah. They like giving the mark allocation according to the number of force vectors that you put there. Alright, so that's 2.2.1. And now 2.2.2 says calculate the magnitude of the acceleration of the system. Show all steps in your calculation. So yeah, what do you think? Do you think this block is going to go all the way to the right? Leaning more towards the 70 kg, or will it go to the left? The 12 kg block. Let's see. Let us calculate considering 2 scenarios for the 12 kg block as well as the 70 kg block. And let's see where that will take us. All right. So if we have a look at the 12 kg block, I feel like it also needs its own, what do you call this, free body diagram. Let's just do it quickly for ourselves. So we have Fg, we have tension, we have the normal force, and that's basically Fg sine 50, and that's Fg cos 50. Okay, so just do it for yourself somewhere on your paper so that, yeah, it makes things a little bit easy. So if we were to sum up the forces in the x direction, all right, we would say the net force is equal to mass times acceleration. So what is the net force? If we take upwards as positive, then we would say tension minus Fg sine 50 degrees, okay, is equal to Ma. Now let's just put in, we don't know what tension is, mass times gravitational acceleration, and then we have sine 50, and that would be equal to 12 times A. Okay, so that is for the 12 kg block. And now for the 70 kg block, we have a free body diagram over there. Again, we're going to start with the net force being equal to mass times acceleration. So I am going to resolve this into its x and y components. So I have Fg sine 30 degrees. Okay, I don't really need the cos part. Fg cos 30. Okay, so the net force then I will take, actually let's take going to the right as positive. All right, so for the 12 kg block, tension was positive, whereas the parallel component of Fg was negative. In this case, Fg sine theta will be positive. Okay, so we have Fg sine 30 degrees minus the tension minus the friction force and that is equal to mass times acceleration. So if I put in the values, Fg is just mass times gravitational acceleration, so 70 times 9,8. Ooh, I hope everything fits. Sine 30 degrees is a half, so I'm just going to put a half there. And then minus the tension. The friction force, remember, friction force is equal to mu k times the normal force. So mu k, they told us, is 0,2 times the normal force. The normal force is actually equal to Fg cos 30. Okay, sure. Let's see how we fit all of that. Fg 70 times 9,8, and then cos 30 degrees is root 3 over 2. Now let's just check. Yes, root 3 over 2. So root 3 over 2, and yeah, so that is basically that. Let's see. Okay, so we have 70 times 9,8 times a half minus the tension minus 0,2 times 70 times 9,8 times cos 30, which is root 3 over 2, and that is equal to MA. Okay, we don't have space. Oh, we do. We do have space. Which is equal to mass, which is 70, times acceleration. Okay, we're going to have to clean this up a bit because, yeah, it's all over the place. I think let me just say make the tensions equal to each other. So I would say then tension is equal to 12A plus, should I rather try to calculate that? 12 times 9,8 times sine 50. Okay, so that's 90,09. Is there a way of storing this? Shift, store. I'm going to make it A. Okay. So that looks a little bit better, much cleaner. And on the other side, I would say tension. If I take tension to the other side, let's see, so tension is 12A plus that. Now in this case, if I take tension to the other side, I would say tension is equal to 70 times 9,8 times a half minus 0,2 times 70 times 9,8 square root 3 over 2 and minus 70A if I take 70A to the other side. Okay, now let's rather get a... So here there is a lot of room for error, and you need to make sure that you are quite precise and you check your stuff. Root 3 over 2. So that is 224,18 minus 70A. And I am going to store that, shift store B. Okay. So now I have two equations that are much better simplified. All right. So therefore, I would say 12A plus 90,09 is equal to negative 70A plus 224,18. If I take the 70 to the other side, 70 plus 12, that is 82A, which is equal to B minus A. So if I take my calculator and I say B minus my A, no, how do I get the stuff that I stored? Oh my goodness, this better not do this to me. Oh, there it is, 134. Great. 134,09. Okay, great. Now acceleration. Okay, moment of truth. But we don't have, so our answer divided by 82, it should make sense. The answer should make sense. Okay, so we have 1,64. I think this makes sense. Okay, 1,64 meters per second squared. Okay. So yeah, calculate the magnitude of the acceleration of the system. I think that's it. I think we are done. All right. Now we go to the last question, which is 2,3. And it says, okay. Yeah. Oh, should I put direction in the previous question? The acceleration of the system. So I chose going to the right as positive, and it makes sense as well because 70 kilogram box is much heavier than the 12, so I would expect it all to go to the right. So yeah, if they wanted also the direction, I would say to the right. Okay. Now for question 2.3. We'll check the time afterwards. So it says if the angle of the slope BC is decreased to 20, will the frictional force between the block and the slope increase, decrease, or remain the same? Okay, so in this case, before we even answer, just know that your friction force, it's equal to mu, okay, well, in this case, kinetic friction, times the normal force, okay? And so the friction force is actually directly proportional to your normal force, all right? So now, if the angle of the slope decreases, okay? So if the angle decreases, what do I say? Yeah, I'm just going to write it down. So the angle decreases, or the angle of the slope decreases, then your normal force is going to increase, okay? And if that increases, therefore it means that your frictional force, yes, the frictional force then will also increase, okay? So your answer is increase, and then you can explain all of this, all right? So yeah. Okay, and how do we know that the normal force does increase? Well, if you were to take the normal force, your free body diagram, where is it? There it is. We said that the normal force is equal to Fg cos 30, right? So we have 70 times 9,8 times cos 30, and that is 594. Now, if we make it 20, let's see, from 594 to 644. So you see that it actually does increase. All right, so it's 15 minutes and we are done with this question. Let's see, 17 times 1,2. We actually had 20 minutes to our disposal, but we saved time. So now, yeah, we are within time, which is great. It's always good just to time yourself. And that's it for question 2. Question 3. A 25-gram ball is thrown vertically upwards. The ball leaves the thrower's hand 1,3 meters above the ground with an initial velocity of 7,27 meters per second. On its way down, the ball bounces off a balcony at a velocity of 3 meters per second before being caught at its maximum height after the bounce. Ignore all effects of friction as well as any horizontal motion of the ball. Okay, so I'm going to redraw this motion and just put in or plug in the values that I know. Okay, so we're starting at the maximum height where it was caught, and then where there was a bounce. Okay. Yeah, something like that. And then just above there. So we have 1,3 meters, and this would be the ground. Okay. So what do we know? We know that the initial velocity with which it was thrown, it is 7,27 meters per second. When it reaches its maximum height after it was thrown, we know that the velocity is 0. We don't know the velocity with which it reaches the balcony, okay, but we know that the height of the balcony above ground is actually 3,2 meters. All right, and then we know that the velocity with which it leaves the balcony is 3. And then once it reaches its maximum again, we have 0. Okay, so it's always good just to know what's happening and, put in the values so that it's much easier when you start doing calculations. But anyway, let's go to the question. Let's see how many marks this is worth. So it's 14 marks. All right, so if we take 14 and multiply it by 1,2 minutes, we should be spending around 17 at most, 17 minutes on this question. Okay, so let's see how far or how much we can do. So now 3.1 says, define the term projectile. Now remember, a projectile is an object, okay, that is either thrown or dropped. So it's a moving object which can be thrown, which can be dropped, which can be bounced. All right, and this projectile or this object, it moves under the influence of gravitational force only. Okay, so only gravitational force, because we are busy with vertical projectile motion, and we know with such we have free fall, and the only force acting on it is gravitational force. So that's 3.1. Now 3.2, it says calculate the maximum height, 3.2.1, above the ground that the ball will reach after it was thrown in the air. Okay, so basically what we're going to do, we're going to calculate this height over here. And after calculating this height, we're going to add it to the 1.3 meters, because that will be the maximum height above the ground. And now we need to decide, are we taking upwards as positive or downwards as positive? This motion that I've drawn here, it's actually if we took upwards as positive, but let's change things around and say downwards will be positive. Okay, and if we do that, what we're going to do when we calculate, what do we have? We have the initial velocity, which is 7,27. We have the final velocity, which is 0. And we need the height. So let's go have a look at the equations of motion and see what we can use. Okay, so we have final velocity, initial velocity, the acceleration, yes, gravitational acceleration. So we can use this formula, Vf squared is equal to Vi squared plus 2 times gravitational acceleration, delta y. Okay, our final velocity, we did say it's 0. Our initial velocity, because we're taking downwards as positive, we're going to have negative 7,27 squared plus 2 times positive 9,8, and we're going to calculate delta y. And because it's moving upward in this first part of its motion, the delta y that we're going to actually calculate is going to be negative. You'll see that. But like I said, it's going to be negative because we're taking downwards as positive. All right, so we're going to have negative 7,27 squared, and we are dividing by 2 times 9,8. Okay, let's see what we get as our answer. So I'm going to say 7,27 squared divided by 2 times 9,8, and we get an answer of negative 2,70 meters. And like I said, this really just means that it is 2,7 meters upwards. Okay, but we're not done. They wanted the maximum height above ground. Okay, not the height above which it was thrown. So therefore, the maximum height above ground will be equal to 2,7 plus 1,3, and that is 4, I think. Who's going to say that? Yes, it is 4. 4 meters. Okay, so that is it. And now on to the next question, 3.2.2. Now it says, calculate the time that the ball takes until it bounces on the balcony for the first time. So basically, we want to know the time of this motion from the time it was thrown up, okay, until it reaches the balcony. Okay, so there are various ways of calculating this. Should I show you both ways that I'm thinking of? Let's see if we did it this way. Okay, let's go have a look at the equations of motion. If you take the whole motion, okay, so looking at this, if you take the whole motion from the initial velocity up until the time, or rather up until where you're at the balcony, what you can do, you can use this formula, delta y is equal to initial velocity times time plus half, yes, so delta y is equal to initial velocity times time plus a half g delta t squared. Okay, this is the simpler way of doing it, but you must be careful when you calculate your delta y. Okay, that would be the trick with this question. Your delta y, when you consider the entire motion, so remember this height that we calculated here, is 2,7 meters, okay, and we have this 3,2 meters, but if you consider the total height from the ground, let's rather do that, that's actually 4 meters. Okay, so if you take 4 meters, no, actually the first way we're going to calculate it, we need this height over here. Okay, let's also provide this height. So if we say 3,2 minus 1,3, we get 1,9 meters. Okay, we're going to consider this as our delta y. And why is that? Because basically the height going up here will cancel with the height going down there, but you still have this 1,9 going up. All right, so delta y, we're going to take it as negative 1,9. Okay, our initial velocity will be the initial velocity that we know, negative 7,27, because we're starting the motion right here. Okay, delta t, that's what we're looking for, plus half, positive 9,8, and we have t squared. So we're going to have a quadratic formula. So 0,5 times 9,8, that is 4,9. So 4,9 t squared minus 7,27 t, and then plus 1,9. Okay, so you're going to use a quadratic formula where we have t is equal to negative b, okay, plus minus, geez, I need to write down the quadratic equation for myself before I go further. Okay, so you have negative b plus minus b squared minus 4ac, all under the square root divided by 2a. Okay, I have it now. So then we're going to have negative 7,27 squared minus 4a, 4,9 c which is 1,9, and all of that is under a square root, and we're going to divide that by 2a, which is 4,9. Alright, so let's see that t is going to be equal to this, or t is going to be equal to that. Let me just remove my working out over here so that things look a little bit tidy. Oh, by the way, we're supposed to be doing this within 17 minutes. Where am I now? 11 minutes. Okay, we're still good for time. So we have negative negative 7,27. Okay, and then we have, I'm going to do the plus first, and the square root, 7,27 squared. Whether I use 7,27 or negative 7,27 doesn't really make a difference. It's going to be a positive either way because I'm squaring it. 1,9, and then we divide by 2 times 4,9, which is 9,8. So I get 1,14 or 1,15. Ooh, what happened here? Okay, yeah, 1,14. 1,1, let's just make it 1,15 seconds. And if we put a negative there, it's probably going to be negative time, which we don't really consider. Oh, no, it's not. We get 0,33 or 34. Okay, now if you get to an answer like that, what do you then do? What do you choose? I don't think it will be 0,34. That's too little, but we can always double check. Okay, so I said I will look at two ways of doing this. So the one way was to consider the entire motion. The other way is to consider motion dividing it in two. So I will look at the first half and then look at the second half. Okay, and that will actually confirm which answer is correct. I guess that's maybe the trick with looking at quadratic formulas in this case. Okay, so if I were to separate it, I would use this equation. Final velocity is equal to initial velocity plus g delta t. So the initial velocity is 7, negative 7,27. The final velocity is 0 if you have a look at this sketch. Okay, initial is 7,27, final is 0. And what do we have? The height there is 2,7, but we don't need height in this case. So we have 9,8 delta t. So delta t will be 7,27 divided by 9,8. Ooh, okay, I'm with my little one, and she just burped. 9,8. So we have 0,74 seconds for the first portion. And because it's for the first portion, it means that 0,34 seconds cannot be the answer. Okay. So yeah, but anyway, we've started. Let's just finish it off and do the second portion of this motion. And for that, we're actually going to need the final velocity over here. Okay. And then afterwards, we can then use the same equation. Final velocity is equal to initial velocity plus g delta t. So I'm just going to calculate it quickly, and then we'll resume. Okay, now we're looking for the final velocity. So we found the time that it took to go up to its maximum height. And now we're looking for the final velocity here. And the height that we're going to use, remember, the full height from the maximum height that the ball reached up until the ground was 4 meters. And then up until the balcony, we have 3,2 meters. So the height that will be used is 0,8 meters. Okay, so this is the 0,8 meters. And the final velocity that we calculated, or I calculated, is 3,96. Now we go back to our formula. where the final velocity is equal to initial velocity plus gravitational acceleration times delta t. All right, and we're going to use our initial velocity as 0, final velocity is what we calculated, and the time was 0,40. So we're going to take 0,40, add it to 0,74, and we get a total time taken to be 1,14 seconds. So I've shown you two ways of calculating this. The one way where you have two answers, but like we said, this one is the correct 1,15 because of rounding off. Option B was just really breaking it apart and calculating it as you can. Alright, so two ways of doing it. I hope that is good enough for you. Let's check the time. We are at 16 minutes. We should be done with this question. It's all good. Now let's do the last question. It says draw a sketch graph of the displacement of the ball for the entire motion. Okay, so we pretty much have the graph in itself. And like I said, the way I drew it here, it's pretty much for upward, taking upward as positive. Okay, so let's draw it properly. So basically, we were starting at, this is me taking upwards as positive. Okay, so just bear with me. So we know that at 1,3 meters, that is where the projectile was thrown, and then it bounced there on the balcony and then reached its maximum height over there after bouncing. Now what do we know? We know that we're literally going to just take off from our sketch there. So we know that it is 4 meters above the ground when it reaches its maximum, and yeah, let's go take it back. So this portion over here, that is 4 meters. But let's just see, what do they want to see? The height from which the ball is released, that's 1,3, yes. By the way, this is y, measured in meters, and that is time, measured in seconds. The maximum height that the ball reaches, that's 4 meters, yeah, so we already have it over there. The height of the balcony, they gave it to us, it's 3,2 meters, so over there, just indicate the 3,2. And then the time it takes to bounce on the balcony, so this is what we just calculated right now, the 1,14 or 15. Okay, let's just use 1,14. And yeah, if you wanted to also indicate the time that it took to reach its maximum height initially, I think that's 0,74. Okay, and that's it. That's it for 5 marks. But this is when you do it if you took upwards as positive. Okay, what if you took downwards as positive like I did? Okay, I'm just going to show you then. If you took downwards as positive, graph is going to look something like this. Displacement in meters. So we're going to start, remember, negative 1.3. We put it there. And it reaches maximum height of 4. And so it's basically this first graph over here reflected in the x-axis. Okay, so yeah, basically we're gonna have something like that. Okay, this is very exaggerated, but you get the gist. Okay, so over here it will be 1,14, 1,3, and that is 4, and over there it's 3,2. Yeah, definitely not drawn to scale. And if you wanted, you could have also indicated 0,74. And that's it. We are over by 3 minutes. But it's fine. It's all good. 4. When a ball hits and bounces off a surface, it exerts a force on that surface. Grade 12 learners investigated how this force varies over time as the ball hits a force sensor and bounces off. A 50-gram softball was dropped from a height of 1.5 meters vertically above a force sensor connected to a laptop as shown in the diagram. Alright, so that they've already given you the mass in terms of kilograms, which is 0.05. Now, the following graph is obtained from the laptop. So we have a force versus time graph. Okay, and I hope that you know that, the area actually below this graph is actually impulse. Okay, but anyway, let's start with 4.1. So it says, define the term impulse. Okay, so please do not be tempted here to write that it is the change in momentum. It's not, okay, it's not acceptable. So impulse is actually the product of the net force acting on an object and the time that that net force acts on the object. So the time at which it acts is very important, and also the magnitude of that force is important, and you're going to just multiply those two. Hence, they say the product of the net force on an object and the time the net force acts on the object. Okay, by the way, how many marks is this out of? This is actually a question out of 13 marks. All right, so then as you plan ahead, you're going to say 13 times 1,2, and you know you should be spending not more than 16 minutes on this question. Okay, so now 4.2. It says, use the information on the graph to determine the magnitude of the impulse as the ball hits and bounces off the sensor. So we're basically going to get the area underneath the graph, like I had said previously. Okay, so impulse is equal to the area under the graph. And since we have a triangle, we're going to use half base times height. Okay, and our base, we can see that it is 15, but remember we are dealing with milliseconds. Okay, so we should be saying 15 times 10 to the negative 3. And our height, our perpendicular height, is 64,13. All right, Newton. So we're just going to put that into the calculator. 0,5 times 15 times 10 to the negative 3. And multiplied by 64,13. And that gives us an answer of 0,48. And what is the unit? Remember, it's Newton seconds. Don't say second units. Seconds, Newton, sorry. Just, it's Newton seconds. Okay. And then 4,3. So it says, state the magnitude and direction of the change in the momentum of the ball. Okay. So the magnitude of the change in momentum of the ball, it will be 0,48 kilograms meters per second. Okay, and direction of the change in momentum of the ball, well, it will be upwards. Okay, let me not say and. So that's the magnitude, and that's the direction, upwards. Okay, 4,4. If the velocity of the ball just before it hits the force sensor is 5,42 meters per second downwards, calculate the velocity with which the ball will bounce off the sensor. Okay, now what are we going to do here? So basically, if we want to calculate velocity here, we are going to use our formula. Let's just go to the formula sheet and see if I can see it. Yes, the net force multiplied by time is equal to change in momentum. Okay, so I'm going to use that formula. Let me just write it down. net force multiplied by change in time is equal to change in momentum. All right. And the reason why I'm going to use change in momentum, or why I wanted it, is because there's velocity there, before and after, initial and final. All right. So we are looking for the final velocity. So the net force times time, remember that is impulse. We've already calculated that. So that's 0.48. And then with the change in impulse, remember we have the mass, which is 0.05. And then we have our final velocity minus our initial velocity. Okay, so I'm going to take the mass to the other side, 0.48 divided by the mass, which is 0.05. Our final velocity is what we're looking for. And our initial velocity, it is 5.42 downwards. Okay, so if it's downwards, remember we're going to have to factor in that negative. Okay, 5.42. Okay, so now let us see what the final velocity is going to be. 0.48 over 0.05. And then we are going to, the minus and the minus gives you a positive. When we take it to the other side, it will be a minus. Okay, so minus 5.42. Now let us see there. So we have 0.48 divided by 0.05. And we're going to subtract 5.42. We're going to probably get a negative. No, not a negative answer. We're getting a positive answer. Yes, okay, so we have 4.18. For a moment there, I thought we were going to have a negative answer. So final velocity is 4.18 meters per second. And because it's positive, it will be upwards. Okay, it seems like this question is moving quite fast. And then the last question, 4.5. It says the ball is now replaced with a hard ball of the same size and mass. Okay, so the mass is still 0.05 kilograms. Okay. Now, will the force on the force sensor increase, decrease, or remain the same? Okay, what do you think? We're asking, will the force on the force sensor, all right, so let's think about it. What happens to the change in momentum? The change in momentum, will it be affected? Or will it just stay the same? And again, since now we have a harder ball, all right, in terms of it bouncing, will it take less time to bounce or will it take a longer time to bounce? Remember, the softer the ball is, the more or the higher the contact time it is. So here, let's just consider what's going to happen. Our change in momentum, okay, is actually going to be constant. All right, and then because now we have a hard ball, it means that the contact time will be less. Okay, for the ball to bounce off the sensor. All right, and we know that our force is actually inversely proportional to time. And we see it by this equation here. F net, if we take time to the other side, it's actually going to be delta P over delta T. So if this contact time is less, the net force will be higher. Okay, so now coming back to the question, what will happen to the force? Will it increase, decrease, or remain the same? The fact that the time will be reduced, the contact time will be reduced, it means that our answer will be, it will be increased. Okay, and that's because our contact time has been reduced. Therefore, the force will be higher. And that is why if you hit someone with a harder ball than a soft ball, they will feel a lot of pain because the force is a lot. Okay, whereas with a soft ball, It's all good. All right, and that is it for question 4. Yeah. Question 5. A 5 kilogram box moves up an inclined plane AB at a constant velocity of 1,2 meters per second. So constant velocity, no acceleration. When a force F is applied. Okay, so now we can see that on the sketch. 5.1 looks like it's going to be a short question, which is 11 marks. And 11 times 1.2 gives us 13 minutes. Okay, so roughly 13 minutes to do this question. Now it says, calculate the magnitude of the force if the power that is used to move the box up the incline AB is equal to 57,6 watts. All right, so there is a formula that relates power as well as force. Hope you can see it here. Under the topic of work, energy, and power, we have the average power, which is equal to force times the average velocity. Okay, going back to our question. All right, so we have our power, which is 57,6 watts, and force is what we're looking for. And what is our average velocity? Our constant velocity was given as 1.2. And so then the force will be 57,6 divided by 1,2, which then equates to, so we have 57,6 divided by 1,2, which is 48 Newton. Okay, great. And now 5,2. State the work energy theorem in words. I'm surprised they actually asked the theory question later rather than at the beginning. Okay, so what is the work energy theorem in words? Well, basically the net work done on an object by a net force is equal to the change in the object's kinetic energy. All right, so that's basically that. 5.3, the box now slides down slope BC. I foresee a question with a lot of marks. Yes, so now it says if the coefficient of kinetic friction of slope BC in the diagram is above, okay, so coefficient of kinetic friction is above 0.25, calculate the velocity of the block at point C. Okay, so what is the velocity at point C by using the energy principles only? All right, let us see. So we have, what do you call this? Friction, okay? So as soon as you see the words friction or see the word friction, think about non-conservative forces. Okay, so let's see, the work done by a non-conservative force, I think that's where I would start, is basically equal to the change in kinetic energy plus the change in potential energy. And this work done by a non-conservative force will be, the force will be the friction force. Okay, so we have our friction force. Remember, work is force times delta x times cos theta. Okay, and then the change in kinetic energy, we have half mv squared, but we have final velocity squared minus initial velocity squared. Please do not do this. It's not the same, okay? Please, 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 please. All right. So that is the change in kinetic energy. And then now the change in potential energy, you have the mass times the gravitational acceleration. Then you have your final height minus your initial height. So the force of friction, okay, what are we looking for again? We're looking for velocity. So the force of friction did they give us anything? We know the coefficient. Okay, so force of friction, basically it's equal to the coefficient of kinetic friction times your normal force. Okay, and they said it's higher than 0.25, but in this case, honestly, I'm just going to use 0.25. All right, so we have 0.25 multiplied by the normal force. So on the section of BC, I'm just going to draw a free body diagram over there, and that would be your FG. That would be your normal force, and that would be Fg cos theta. So your normal force is equal to Fg cos theta. So Fg, basically the mass, which is 5, times gravitational acceleration. So Fg, and then cos theta. So we're going to have cos 32 degrees. Okay, and I'm just going to get what that value is. 0.25 multiplied by 5 multiplied by 9.8 multiplied by cos 32. Probably going to store that answer somewhere. Okay, and so that is 10.39 Newton. Okay, so that is the force of your friction. Okay, I'm just going to store this. So now friction force 10.39. Now delta x, what is the distance that it goes? Okay, so if we have, there are all these sub calculations that I need to do. Yeah, okay, so firstly it was to get the friction force. You'll write it out nicely in your workbook. But if we get the length of BC, we're going to have to use Pythagoras. No, not even Pythagoras. We're going to use our trigonometric expression. So we have 1,6 over here, 32 degrees, and we're looking for the hypotenuse. Okay, so sine 32 degrees is equal to 1.6 over, I'm just going to say BC. Therefore, BC is equal to 1,6 divided by sine 32. So 1,6 divided by sine 32. And that is equal to 3,02. Okay, so that's our delta x, 3,02 meters. I'm also going to store that as B. Okay, and then cos theta, well, I'm going to take that as 180 degrees because it's friction acting in the opposite direction. Okay, and then we have half mass. Mass is 5 kilogram. We're looking for the final velocity. The initial velocity is 1,2. And then we have our mass, 5 times 9,8. So we have our final height, which is 0, and our initial height, which is 1,6. Okay, this is quite loaded. Let's just start first with the left-hand side. So we have A times B times cos 180, which is just -1. And we have a negative 31,37. Okay, let's see how far this will take us. And then on the other side, I think let me just store that, shift store C. And then we have 0,5 times 5. So we're gonna have what? 2,5 final velocity squared minus, so we're going to have 1,2 squared, so minus 3,6, and then plus 5 times 9,8, times negative 1 comma 6. So that's negative 78,4. All right. Now let us take everything, or rather, let me just do this. We have negative 2 comma 5. Final velocity squared. And then if I say negative 3 comma 6 minus 78 comma 4 plus 31 comma, oh, let me just say C. Okay, actually no, I should have said minus C. Yeah, because I'm expecting a positive. Oh no, still gonna be a negative answer. But yes, 50,63 makes sense. Negative 50, guys, you must always question your answers, okay? Because negative 3,6 minus 78,4, it's probably negative 80 something, and negative 80 something plus 30 something should be 50, negative 50 something. Okay, so yeah, now we take this, we divide it by negative 2 comma 5, and that is final velocity squared is 20,25, and now the final velocity, if we square root that answer, whew, yo, we have been laboring. Okay, so we get 4,5 meters per second. Okay, so that is the final velocity. And where are we now? This is 5,3. Oh, we're done. Okay, yes, we are done. All right, thank you for tuning in for question 5. And we did it under 13 minutes, so that's good. Question 6. In the diagrams A, B, and C below, the wave patterns are shown for the sound of a siren from an ambulance and a stationary observer. The observer remains stationary in each case. Now you can see for A, we have the source of the sound, and we have the observer there, and pretty much the lines are flowing out equally. Okay, and that tells you that both the source and the observer are stationary. If you look at B, the wavelengths are very compressed close to the observer. So that means this ambulance is actually moving closer to the observer. And for C, we can see that the wavelengths close to the observer are actually spread out. All right, the frequency is less, meaning that it is moving, or the ambulance is moving away from the stationary observer. Okay, I hope this is very clear. Now 6.1, it says define the term Doppler effect. You know what, in most questions I see they always ask this, so please make sure that you know the term Doppler effect. Okay, and what is it? So basically it is the change in frequency of the sound detected by a listener. Okay, and how that listener detects that sound, well, that's because probably the sound source is moving relative to the listener. Either both of them are moving or one is moving. Okay, so anyway, let me just wrap it up and say it is the change in frequency of the sound detected by a listener. Okay, and that is because the sound source and the listener have different velocities relative to the medium of sound propagation. In this case, the medium would be air. Okay, if it was in water, the medium would be water, and so forth. But please make sure you know the definition. And now 6.2, for questions 6.2.1 and 6.2.2, state either A, B, or C. Okay, so for 6.2.1, for which the sound source is stationary, okay, we did discuss it, so it's A. And 6.2.2, the sound source is moving away from the observer, so that is C. Okay. Now 6.2.3 says, give a reason for the answer in 6.2.2. So why are we saying that the sound source is moving away from the observer? Well, basically, the wavelengths, we have seen that they have increased, okay? So for B, it was, something like that. So the wavelengths are quite small. But in picture C, we can see this being the wavelength. The wavelengths have actually increased. Okay, so if your wavelength has increased, the higher or the bigger your wavelength, the lower your frequency, and as such we can see that in this case it's moving away. Okay, so the frequency of the waves reaching the observer decreases as the wavelength increases. Okay, we'll leave it at that. And then 6.3, it says, if the ambulance is moving away from the observer at a speed of 25 meters per second, so the speed of the source of sound is 25 meters per second, and the frequency of its siren as heard by the driver is 900 hertz. Okay, so the frequency really of the source is 900 hertz. Calculate the frequency observed by or heard by the observer. So frequency of the listener is what we need to calculate, and we know that the speed of the listener is 0 because they're stationary, and then the speed of sound in the air is 340 meters per second. Okay, so we're going to use the Doppler effect formula. Is it given in the formula sheet, or is it something that you have to know? Hopefully not something you have to know. So it says the frequency of the listener is equal to the speed of sound in air, plus minus the speed of the listener and speed of the source times frequency of the source. Okay, let's go back to our question. All right, so the frequency of the listener is what we're looking for. In this case, speed of sound in air is 340. The velocity of the listener is 0, so we don't even bother writing anything further. And then we have 340. All right, and what do we have, plus or minus? Well, we have plus. And then the speed of the source, we did write it down. It is 25 meters per second. And the frequency of the source is also given as 900. So this was a straightforward calculation, nothing tricky there. So that is quite nice. So very lenient with you guys with this paper so far. It's not that bad. Okay, so now we have 838.36 hertz. Okay. And that was 6.3 for how many marks? 5 marks. And now 6.4. It says the hydrogen spectral line from the sun has a wavelength of 656 nanometers. Now, if this spectral line from a nearby star has a wavelength of 657, so it has increased from 656 to 657. What can we conclude about the motion of the star in relation to the sun? So it is kind of further away from the sun. Okay, so what can we say? We can say actually that this star is moving away from the sun. Okay, I mean, because the wavelength that we see, 657, to the star compared to the sun, which is 656. So the star is moving away from the sun, and because it is moving away, I mean, the wavelength increased. Okay, so therefore we have a red shift. Okay, so the wavelength that we have is red shifted. Okay, and we can then say that the observed wavelength of the spectral lines of the hydrogen atom from the nearby star is longer, which is what we were basically saying here. The wavelength is longer. Okay. Than the wavelength. So the wavelength is longer. Let me just actually write that down so that it makes sense. So the wavelength is longer for this star compared to that of the sun. Okay, so I think that is worthy of 30 marks, just to comment on the wavelength, that we have a red shift, and we can then say the star is moving away from the sun. And that concludes question 6. And we are within time. Yes, we should be. So somewhere in the paper, if you spend a lot of time maybe in question 1, I guess some other questions you can make up for that time. Okay. Question 7. An investigation was carried out to show how the electric field varies at a fixed distance away from a positively charged sphere. To achieve this, a positive charge Q was varied, and the respective electric field E was measured. The following table of results was obtained. Now we can see a trend here that as you increase the charge in nanocoulomb, the electric field as well increases. Okay, now 7.1, let's just answer the questions. The questions below refer to the table and the investigation that was conducted. 7.1, define the term electric field at a point. All right, so the electric field at a point is the force experienced per unit positive charge at that point. Important not to forget, it's that positive word. The force experienced per unit positive charge. Do not leave out positive, okay? So if you say per unit charge, you'll get 1 mark, but if you say per unit positive charge, then it secures your other mark. 7.2, draw the electric field pattern for a positively charged particle. Okay, so let's say you have a positively charged particle, and remember, as you draw the electric field lines, they're actually perpendicular to the surface, if I could say, of the positively charged particle. All right, and with a positively charged particle, you have the electric field lines, pointing outwards. Had it been negative, it would be pointing inward. Okay, and then 7.3. By the way, this is out of 15, né? And we should be spending around, 18 minutes on this question. Okay, and we're already at 2 minutes. Okay, so plot the graph of electric field versus charge. Use the graph paper provided at the end of the question paper. Let me just provide graph paper for myself. But which one will be on the y-axis and which one will be on the x-axis? Remember, with a charge, basically you vary the charge and the electric field is dependent on the charge. So electric field will go on the y-axis and the charge will go on the x-axis because it's independent. Okay, and one thing they have kept constant here is a fixed distance. Okay, but anyway, yes, I'm gonna just pause now, get myself graph paper, and then we'll plot. Alright, I have my graph paper, and now let's plot. So for a charge of 1, by the way, this is Q in nanocoulomb, and that is electric field, kilonewton per coulomb. Alright, so 1, so this is 1 here, and 4 for electric field. So let's do that. and then 4 and 16. Okay, 4, 16, yeah, somewhere around there. And then 8 and 32. Okay, 8, 32, somewhere here. What I'm doing is probably not really to scale, but we're trying. Okay, 11 and 44. Okay, let's see. 11:44. Probably around here somewhere. And then 14 and 55. 14, 55. Alright, and now we can draw a straight line, or the line of best fit. I tried. Okay, let's try that again. You'll have a ruler with you, so that should work out fine. Okay, I think it's fine. Alright, so that is our graph. We've drawn it. And then now it says, let's just remove all of these lines. That was just for drawing purposes. Okay, now 7.4.1. It says, before we even go there, let's see, when you draw a graph, where do you get the marks? So basically, if you have a scale on both axes, which we do, and then points plotted correctly, we did. Now points, line of best fit, we try to draw one, and then we have it. So yeah, and then you actually draw a graph. And also, if you put the dependent and independent variables correctly. So yeah, okay, let's move on. 7.4.1, it says use the graph only to answer the following questions. Identify the controlled variable in this investigation. So they did say in the question there, or in the introduction to the question, that an investigation was carried out to show how the electric field varies at a fixed distance away from the positively charged sphere. So that's the one thing that you've controlled, all right? And that is the fixed distance. And then 7.4.2, it says identify the dependent variable in this investigation. Dependent, remember, it's on the y-axis. Independent is on the x-axis. So on the y-axis, we have electric field. Okay, and then 7.4.3, determine the fixed distance between the charge and the point where the electric field is measured. Okay, distance. If we have a look at our formula for electric field, did I pass it somewhere? Geez, don't I have... I think there are portions of this paper that are missing. Yeah, but anyway, so the electric field, yeah, actually the electricity portion here is missing in the formula sheet, but I think in your formula sheet everything will be there. So let's just work from memory. So electric field, don't know if you remember, it's actually kq over r squared. Okay, and then what we're looking for is the fixed distance between the charge and the point where the electric field is measured. So basically we're looking for r, not r squared, but r. Okay, and on our y-axis we have E, so we can use E. We have K, it's a constant. We have Q, so we can solve for R. So if we write everything in terms of R, we can say R squared is actually equal to KQ over E. Okay, and R will actually be the square root of K times Q over E. Now, I don't know if you realize this. Let me write it down like this. K is actually Q over E. No, not equal to K. K is not Q over E, but K, you can write R as K times Q over E. Okay, and what we can do then is, let me see. Yeah, so what we can do is get a value of Q and also get a value of E. All right, and the reason why I separated it, I thought we might actually use gradient. Okay, where the gradient is actually delta y over delta x, which actually would be delta E over delta Q. But it's fine. We don't really have to, but I think it's yeah, let's rather use delta Q over delta E, because we have 2 points. It would work better than just using 1 point. Okay, and which 2 points do we want to use? I say let us go. So K, we know that it's 9 times 10 to the power 9. For delta Q over delta E, so Q, let me choose the 2 points that look like both of them are on the line. It is, what is it, 11, or rather 8 and 14. Okay, so let's just choose these 2 values over here. Okay, so for our delta Q, we're going to go with 11 times 10 to the 9, or negative 9, minus 4. No, what did I choose? I chose 8 and 14, not 11. Okay. 8 times 10 to the power negative 9. Start with the last one. So 14 times 10 to the power negative 9 minus 8 times 10 to the negative 9. That's delta Q. And the respective E's that we have there, we have 55 times 10 to the 3 minus 32 times 10 to the 3, because it's kilo Newton Coulomb. And all of that, it's under a square root. Let's try that again. All right, let's calculate then. So we have 9 times 10 to the 9, and then multiplied by 14 times 10 to the negative 9 minus 8 times 10 to the negative 9 all over 55 times 10 to the 3 minus 32 times 10 to the 3. Okay, and we're getting a value of around 0,048. I will round it off to 0,05, and that, what would the unit be? It would be meters. Okay, so that is the distance fixed distance between the charge and the point where the electric field is measured. All right, and I think that concludes 7.4.3. And how long did we take? 13 minutes, yeah, which is quite good. Question 8. The battery in the circuit diagram below has an EMF of 6 volts. I'm just going to write that down. EMF 6 volts and an internal resistance, so small r, 0.4 ohm. Right, so we see the circuit here. Okay, so 8.1, with both S1 and S2 open, the switches, give the reading on voltmeter V2. Okay, so whenever you have your switches open, the voltmeter will actually read what's on the EMF. Okay, because it's actually parallel to the EMF. Okay, so in this case it would be 6 volts. And 8.2, with only S1 closed, so we still have S2 open, the ammeter records a reading of 0.75 amperes. Okay, let's see, with S1 closed, so thereby S2, all right, okay, 0.75 amperes. Explain the meaning of 0.75 amperes. Well, if you think about it, current I is equal to Q over T. Okay, so basically when a charge of 0.75 coulomb travels in the circuit in 1 second, so that is what 0.75 amperes mean. Or you could say we have 0.75 coulomb per unit time. Okay. All right, yeah, we can do that. So 0.75 coulomb per unit time, or you could say the rate at which, okay, because as soon as you see T there, or delta T, delta Q over delta T, as soon as you see delta T or T, think about, what do you call this, the rate. Think about rate. So you could say the rate at which 0.75 coulomb flows. Okay, so that is what you would explain 0.75 amperes to be. Now 8.3.1, with only S1 closed. Okay, so basically there wouldn't be any flow of current through S2 because that would be open, so it'll only go through resistor R and resistors 3 and 1. Okay, but anyway, with only S1 closed, calculate the external resistance of the circuit. All right, so remember we have EMF is equal to the total current, then you have the external resistance and the internal resistance. We have the EMF, it's actually 6. Then we have the current, because they did say when S1 is closed, there's a reading of 0.75, right? So 0.75, that's our external resistance, and our internal is 0.4. So our only unknown here is the external resistance. So we're going to have 6 over 0.75 minus 0.4 is actually R, external resistance. So if we calculate that, we have 6 over 0.75, okay, and minus 0.4. So we have an external resistance of 7.6 ohm. By the way, what is this question out of 17 marks? As expected. Electric circuits take up a lot. Okay, so we should be done with this question in 20 minutes, and we're already at 4 minutes. Okay, 8.3.2. Now with only S1 closed, calculate the resistance of resistor R. So we have already calculated the external resistance, right? So now we know that the external resistance is equal to the resistors in series and the resistors in parallel. Okay. So now let's see which resistors are in series. So we have 1 and 3 that are in series, so we can then make it 4 ohm. And then we have that resistor, that's what we need to determine. And then we have the 4 ohm resistor. Okay, we have our current there, we have our battery. And yeah, that's our simplified circuit. So we have resistors in parallel and those in series. So let's just get what the ones in parallel are. So basically have 1 over R plus 1 over 4. Okay, and yeah, so basically I will have 4R and then 4 plus R and 1 over R parallel. So basically R parallel is 4R over 4 plus R. So external resistance is equal to the parallel plus the series. The external resistance we calculated was 7,6. The parallel resistance is 4R over 4 plus R. Okay, and then the resistor in series there is 4. Okay, so 7,6 minus 4, we get 3,6 multiplied by 4 plus R is equal to 4R. So we have 3,6 times 4, which is 14,4. And then plus 3,6R is equal to 4R. So 4 minus 3,6, that is 0,4. Ne? Yeah, 0,4R is equal to 14,4. So now R is 14,4 divided by 0,4, and we get 36 ohm. Wow, so high in relation to the other resistors. Okay, so we have resistor R. It's also 3 marks. And now 8.4. It says S1 is now opened and S2 is closed. Okay, so if S1 is opened, the current going through R will just stop. There won't be any current going through R. There will also not be any current going through the 1 ohm and the 3 ohm resistor. So the current will only flow through the 4 ohm resistor and also flow through the switch S2. Okay, so S1 is now open, S2 is closed. How will the power dissipated by the 4 ohm resistor change? Okay, how will the power change? How was it before? So before, when we had S1 closed and S2 open, remember we had a current of 0,75. And what is power equal to? Power is equal to VI, right? But there's another variation. So if we say V is equal to, so it's basically I squared times R. Okay, because V is equal to I times R. Okay, so previously we had 0,75 amperes flowing through, multiplied by that 4. Now if we close, or how we can actually say it is if S1 was previously closed and S2 was open, yeah, the current would have been divided, right? There's a lot of resistance, basically. But now with S1 open and S2 closed, there isn't much resistance, okay? And you can see here, if there isn't much resistance, if your resistance has decreased, and your current probably will increase, which means that your power also increases. Okay, so let's write this down. What will happen to the power dissipated by the 4 ohm resistor? Firstly, it will increase. Okay, and why is it increasing? It increases because we've recognized that our external resistance has decreased, right? And because it has decreased, the external resistance, our current then increases. Okay, and according to this equation that I've indicated over here, okay, power is actually directly proportional to current squared. So if your current is increased, then ultimately your power will also be increased. Alrighty. Now we get to the other portion of question 8. It says grade 12 learners conducted an investigation to determine the internal resistance of a battery. Okay, the circuit used is shown below. By varying the rheostat settings, the corresponding values of the circuit current and the potential difference V2 were recorded. So this is those graphs. I did a video on it well, not now, but recently. I'll just show you the video that you can access. But anyway, the results obtained were used to plot the graph below. So we have potential difference versus current. So basically, you're already there on our YouTube page, you'll see that there's the electric circuit graphs made simple that I do cover. All right. These damn adverts. Yeah. But basically, yes, you can actually go through it. And I don't know how to mute. I'm not seeing the mute.
A fresh way to shop, pick and pay. Just tap, tap, ASAP. Our freshest groceries, delivered fast, easy.
Yeah, but please do watch the adverts so that we can get money. Okay, so why isn't the video playing? I just wanted to fast forward to this type of graph. And, alright, this thing is not playing. I hope another advert is not going to play. Alright, there we go. So electric circuit graphs.
And I thought I would make this quick video. I don't know if it's going to be quick. But yeah, I'm hoping.
Alright, but you know what? It's fine. You guys can watch it in your own time. I think let us just get to this question and answer it because internet connection is not so strong. Okay, so what I wanted to show you through that video is this graph that I did cover, where we have potential difference or terminal potential difference versus current, and it's a downward slope. Alright, so you're going to write down your equation for the EMF, which is the terminal potential difference or external voltage plus your lost volts. And if you rearrange that equation, you can actually write it in terms of y is equal to mx plus c, where your gradient is the negative internal resistance, your x would be I, and your c, which is your y-intercept, would be EMF. Okay, so if you were to, let me actually erase this and draw it again, this time let it touch. So at that point there, that's where you can read off your EMF, and if you wanted your gradient would be negative the internal resistance. Okay, and your x-intercept will basically be I, your current. Okay, but anyway, yes, let us go on and answer the questions. So for 8.5.1, so from this graph, deduce the EMF of the battery, and you can see it's only one mark because it's something that you can read off, and we can see it's the y-intercept, and in this case we get 4.5. Okay, I hope that you see it and I hope that it's clear. So it's 4.5 volts. And then 8.5.2, calculate the internal resistance of the battery. The internal resistance of the battery is the gradient. Okay, or let me rather write it like this. let me say the internal resistance is the gradient. Okay. Ooh, the little one is having exciting dreams, I don't know. And our gradient here, delta y, which would be delta v over delta x, which is basically delta I. All right. Now let us go and choose two values that we can see. I will, on the y-axis, I'll choose 4.5. Yeah, so let's go with 4.5. And the current there is 0. And then let's choose another point that is not difficult. So I'll go with 3. And the current there, for a volt, potential difference of 3, I get the current to be 2.5. Okay, so let's do this. So we have 4.5 minus 3 all over 0 minus 2.5, and we get negative 0.6. Okay, but remember, you can't have a negative internal resistance, so we'll just say the internal resistance is 0.6 ohm. And wow, we're done with the question. Okay. Yeah, we're done. All right, and we did this in 16 minutes. Okay, good. Second last question, question 9. So it says, study the diagram below and answer the questions that follow. Okay, so without even looking that deep into the diagram, I can see that I have 2 slip rings, and that should yeah, give us a clue with what we're working with here. So let's go to 9.1. So it says, what type of generator is shown in the diagram above? Motivate the answer by referring to the names of specific components in the diagram. So slip rings, we normally find them with alternating current, whereas the split ring will be for DC. Okay, so here what type of generator do we have? We have an AC generator. And motivate the answer. Well, because we can see that we have 2 slip rings. Okay, so the slip rings give it away. If we had split ring commutator, then it would be DC. 9.2, indicate the direction in which the current will flow. So here, because we have a generator, we're going to use our right hand rule. And I'm going to pause to feed the baby. So if we have a look at the side AB, you can see that this thing is going clockwise. Okay, so the thrust on AB is actually going down. So your finger, your right hand finger, will be pointing down and then north to south. So as your right thumb, did I say right finger? Right thumb, as your thumb is pointing down, your index finger will be pointing to the right, okay, from north to south. And then where is your middle finger going? You can see that it's actually going in the direction of B to A. Okay, so that's the current that's flowing in this direction of the direction in which the current will flow is from B to A. Okay, now 9.3. The following graph is obtained from an AC generator. So we can see I max is 15, okay, or negative 15, although the minimum is negative 15, maximum is positive 15. And then it says for 9.3.1, how many rotations of the coil are shown in the diagram? Okay, if you're not sure, just check for yourself where there is a full wave, and you can see a full wave is there. Okay, this is the full wave, and then we have half the wave. All right, so basically we have 1.5 turns. Okay, and then 9.3.2, By the way, this is out of 17. This is the most I've ever seen question 9 counting. It's normally less. So again, we have around 20 minutes. So, but the way we're going, it's quite fast. 9.3.2, define RMS current. All right, so the RMS current is the alternating current which dissipates, okay, the same amount of energy as an equivalent direct current. I repeat, the RMS current is the alternating current which dissipates the same amount of energy as an equivalent direct current. And now my battery wants to die. So calculate the average power that can be delivered by this generator to an apparatus with a resistance of 30 ohm. Okay, so firstly you're going to use your formula. Imax is rather IRMS, not Imax. IRMS is equal to the maximum current divided by root 2. Okay, and our maximum current, we've seen it, it's 15, okay, divided by root 2. So our IRMS will be, if we have 15 over root 2, 15 over root 2. So we get 10,61 amperes. Okay, so we're going to hold on to that answer because we're looking for the average power. And then average power is equal to your I squared, but this is now IRMS squared multiplied by the resistance. So we have 10,61 squared multiplied by the 30 ohm. So we're going to say answer squared multiplied by 30. And that, okay, now I need to start. Okay, let me say 15 divided by root 2. Okay, that's 10,61 and I square it. So I get 112,5 and 112,5 multiplied by 30 is 3375. Okay, 3375 watts. Okay, we're almost there. Last question now, 9,4. So it says an electric hairdryer is rated at 2,200 watts. So we have the power at 240 voltage. Okay, so that voltage that they have given us, it's actually VRMS. All right, 240 volts. Assume that the hairdryer is a pure resistor. Calculate the maximum current that flows through the hairdryer. So we're looking for I max when it is used. Okay, so let's see if we can get, so we have P average. We can use the formula where we have the voltage VRMS multiplied by IRMS, and we have our average power, which is 2,200 watts, and our VRMS is 240. So our IRMS will be 2,200 divided by 240. 2,200 divided by 240. So we get 9,17. Okay, that's our IRMS, and that's in amperes. And then in order for us to get Imax, so we're basically going to use this equation. IRMS is Imax. So IRMS is equal to I max over root 2. So I max is equal to root 2 times I RMS. Okay, so root 2 times 9,17. So I'm going to take that, multiply by root 2, and we get 12,96. 12,96 amperes. Alright, and we are done with question 9. Alright, and that didn't take us that long, not even 10 minutes. So yeah, see you guys question 10. Finally, at the last question, question 10, and it says the diagram below shows a photo tube that was used to demonstrate the photoelectric effect. The demonstration was carried out by shining light from a red, a green, a blue, and an ultraviolet light source onto the surface of the photo tube. The results were recorded in the table below. So we can see for red, there was no reading on the ammeter. Okay. There were no electrons flowing in the circuit. And from green to ultraviolet, there is a reading on the ammeter. So now 10.1. Explain what is meant by the photoelectric effect. Okay, so the photoelectric effect is a process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. It's important that the surface is metallic because you have electrons, a sea of electrons on the surface of a metal. All right, and if you have light of a suitable frequency that is higher than the threshold frequency, then you will get those electrons ejected. So just to recap, the photoelectric effect is a process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. Okay, so that's 10.1. And we just answered that. Now 10.2. Explain why there is no reading on the ammeter when the red light is used. Alright, so remember red light has a higher or rather longer wavelength, but lower frequencies. Okay, so it could be that the frequency of the red light is actually less than the threshold frequency. Okay, I'm gonna write it out. Threshold frequency. Okay, so it could be that. So it doesn't have enough it doesn't have enough energy to eject electrons from the phototube of the metal surface. Okay, and then now 10.3, it says, for the following statements, use increase, decrease, or remains the same to complete the statement. So 10.3.1, it says the kinetic energy of the photoelectrons when ultraviolet light is shone onto the surface of the phototube instead of green light. So we know that ultraviolet light has a higher frequency than green light, okay? So the kinetic energy of the photoelectrons increases. It increases when ultraviolet light is shone onto the surface. All right, and then 10.3.2. The reading on the ammeter, when green light of higher intensity is shone onto the surface of the phototube. Now explain this observation. So the reading on the ammeter will increase, or it increases when green light of higher intensity. So the trick here, or the key words here, are higher intensity. So when you have a high intensity, then the reading on the ammeter will increase as well. Okay, so it increases, and we need to explain this observation. When the intensity of light increases, the number of photons per second of light striking the phototube will also increase. Okay, increasing the intensity of light also increases the number of photons per second. All right, and yeah, again, also this will increase the number of electrons ejected per unit time, and therefore the reading on the ammeter will increase. All right, so let us answer the last question. Is it? Yes, it is. So now it says the cathode is made of copper with a work function of 3,52 times 10 to the power negative 19 joules. Okay, so work function is equal to 3,52 times 10 to the power negative 19 joules. If ultraviolet light with a wavelength, so we have a wavelength of 390 nanometers. So if ultraviolet light with a wavelength of 390 nanometers was used during demonstration 4, this is with ultraviolet light, calculate the speed of the photoelectrons that were ejected. Okay, so first we're going to start, let's look at the formula sheet. Okay, we're going to start with this formula here, where E is equal to the work function plus kinetic energy, or the maximum kinetic energy. Okay, and we know that E is actually equal to Planck's constant and speed of light, c, over the wavelength. Okay, and we have our work function there. We're going to just substitute everything together. Okay, let's go back to the question just to make sure we're answering the question. So calculate the speed. Okay, so we're looking for EK max at this point in time. That will eventually give us V. All right, so H is Planck's constant, which is 6,63 times 10 to the power negative 34. All right, multiplied by C, which is the speed of light. So it's 3 times 10 to the power 8. And that is divided by the wavelength, which is 390 nano. So nano is times 10 to the power negative 9. All right. And then our work function, we already have it there. It's 3,52 times 10 to the power negative 19. And then we have the kinetic energy, the maximum kinetic energy. So it's half mv squared. Actually, we can substitute the mass already, because we have the mass of the electron, which is 9,11 times 10 to the power negative 31. So that's half mv squared. So v is actually our unknown. So now we have to rearrange. So now we have to rearrange this equation such that velocity becomes our subject of the formula. Let's see how we're gonna do this. I think let's just calculate for now on the right side of the equation. So we have 6,63 times 10 to the negative 34 multiplied by 3 times 10 to the 8 over 390 times 10 to the power negative 9. And so we get 51 times 10 to the power negative 20. Okay, that helps us. So we have minus 3,52 times 10 to the power negative 19. And then all of that will be divided by a half, 9,11 times 10 to the negative 31. and we will square root it to get what the velocity is. Okay, so let us see how this pans out. So we have a square root, we have our answer, minus 3,52 times 10 to the power negative 19, and all of that is divided by a half times 9,11 times 10 to the power negative 31, and we get it to be 588,958,04 meters per second. Okay, does this make sense? It does. This is an electron. It's moving very fast. So not expecting to get very low values. And if you wanted to simplify further, you could have said 5,89 times 10 to the power 5 meters per second. So basically we're moving this comma 1, 2, 3, 4, 5 spaces to the left. Okay, and this is our answer. And are we done? Are we officially are we officially done? Yes, we are. 10.4, and that is paper 1. I hope that the preparations will go well for your finals, and may you do your best and get the best marks. Don't forget to like our videos and also subscribe to our channel. Thank you.